Hey, hi, hello. Let's take a look. Thank you for clicking on the video. This will just be a quick introduction video, just recapping a little bit about what we've covered or the concepts within Reconstitution. So Reconstitution is you've got medication that's been rendered into a powder for preservation purposes. This is one of those vials where you poke a syringe in, withdraw, or maybe it's an amoxicillin bottle where it's like you'll mix it with just water. You open the top off, pour some water in, or maybe your other solvent that you use to mix this together. And we're going to turn this powder into a suspension, or a liquid, a solution, and we'll go ahead and use it for administration or for medical use. It's great for storage purposes. So if we were to take a look, and some medication actually, after you do reconstitute it, goes bad after a certain period of time. So this is a great way to preserve the medication. If we were to take a look and say, okay, well, what does this really mean for us? We've covered in the past that if you were to have 5 grams of sugar, okay, and you put it in 5 mLs of water, then you have 5 grams per 5 milliliters. And if you were to withdraw from there 1 ml, then that would equal 1 gram's worth of sugar. What else could it be? If you withdraw 1 milliliter, it has to be 1 gram. It can't be 5 grams. There's no way you'd pull out 1 milliliter and that's 5 grams of sugar, because everything else is all sugar too. So if we were to look at it just from a basic math standpoint, for every 5 milliliters, I've got 5 grams, 5 mLs, or let's do 0 mLs here, 5 mLs is here, and I've got 1, 2, 3, 4, and 5. And I've got 5 grams. For every milliliter, I've got 1 gram. So when I extract 1 ml, that's 1 gram. Okay, that works fine when it's basic math, when it's easy math, but when it comes to more complicated scenarios, or you're working with weird numbers, 3.375, 4.296, it gets kind of foggy. So what we're going to do is we've got DHQ. And DHQ is helpful because it really puts everything in place for us. D is our desired. In this case, it was 1 ml. Or I'm sorry, in this case, it was 1 gram. We needed 1 gram of amount of sugar from this work here. And if we've got the desired up here as 1 gram, then we've also got here our have, or our supply. With our supply, that's what strength you have. In this case, we had 5 grams per 5 mLs. That's our strength. We'd isolate H would be the value up top, and then Q is our quantity. It's interpreted as amount, quantity, or even better, we can interpret it as our per quantity. So we have 5 grams per 5 mLs, 200 grams per 1 tablet. And here our X, that is our amount of solute. And so if we were to re-express everything we've done here into DHQ, our desired is 1 gram over our have, 5 grams, times our Q, our per quantity, 5 mLs, we have 5 grams per 5 mLs, and this will give you our amount of solute that we need. So 1/5, 1/5, times 5, just going straight across. These cancel out. You've got one over another. You've got 5 mLs. This is saying, oh, I'm sorry, 1 ml. I can't do basic math, I guess. You could run it through a calculator. If I've got 1 divided by 5, that's 0.2 times my 5, I've got 1. Let's go and change this mode. Okay, so that's the basic math foundation of it. It works really well for what we're doing. We've got this note card here summarizing it, so we'll keep it through the remainder of the videos. Now, where it gets kind of hairy is that when it comes to dilutions, you've got certain things that don't 100% mix. So We call this our displacement factor. In the example of the sugar, I've got 5 grams in 5 mLs. Gives me my 1 gram per 1 ml. Certain medications don't 100% dissolve in water. So if you've ever looked at let's do an example of a beaker or a graduated cylinder, and of this substance, let's say you've got 1 milliliters worth of powder. And you'll say, well, it's weird that I've got 1 milliliters of powder. Usually it's in grams. But if you weigh, let's say you weigh 1.3 grams of medication. It's a dry powder. And then you pour it into your graduated cylinder, and it takes up about 1 milliliter. If you add 4 milliliters of water, it could be 5 ml if this medication doesn't 100% dissolve in water. You might end up with, if you've added 4 ml, you might end up with 4.2, 4.3. You might have some left over that didn't dissolve. That doesn't go for all medication. And for any questions you'll see, any examples you have, any application in the real world, you might see on a bottle, I've got 500 grams. If I add 500 mLs, you might say, okay, that's easy, 500 grams per 500 mLs, that's my concentration. No, when you actually do it, they might tell you, okay, it comes out to be, 400 grams per 500 mLs. With the total amount being, let's say, in the vial, 550 mLs, with the 5 mLs coming from that dry powder. So it depends on the medication. Some are 100% soluble, some are not. In the past, we used the examples of sugar, right? And that dissolves pretty well. But what if I was going to do maybe coffee? Or we know sometimes baking soda doesn't dissolve 100%. With the coffee, you'll have the coffee floating around, you'll have the flavoring, you've got the actual grains at the bottom, the gradients. For baking soda, it might dissolve, you might see particles suspended everywhere, mixed with it, turning it into a solution. I use the word suspended, that might not be entirely accurate. Because some of it will be floating around, some of it will be dissolved in it. If it's suspension, it's floating around in pieces, not mixed. But if it's a solution, it's mixed. So keeping this in mind, we'll go and take a look at some problems.